Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Electrolyte Materials for Redox Flow Batteries, Non-Aqueous Electrolyte from the paper Energy Related Materials. So students, let us see what are we going to study in this module. From this module, you may get to know about the following. Number 1, role of non-aqueous electrolyte material in RFPs. Second, types of non-aqueous electrolyte materials. Third, working mechanism of various non-aqueous electrolytes in RFPs. So let us start with a brief introduction about non-aqueous RFPs. Several RFPs are designed and developed for commercial applications which are primarily based on aqueous chemistries. These RFPs were successfully installed by research organizations and industries in many countries of the world. In spite of their remarkable success of aqueous RFPs, these batteries showed low energy density of about 20 to 50 watt-hour per L due to aqueous electrolytes. The energy density of a RFP depends on cell voltage and the solubility of redox compounds. For aqueous RFPs, the cell voltage is limited, that is, it is around 1.2 volts, by the narrow electrochemical window of water that breakdowns with less than 1.5 volts. However, the non-aqueous RFPs utilized organic electrolytes that after significantly wider electrochemical window, example above 5 volts, and larger solubility for redox compounds, thus they provide larger value of energy density. Further, as non-aqueous RFPs are organic solvent that provide low freezing point, hence, due to this reason, their working temperature can also be extended. The basic concept of non-aqueous RFPs was first proposed in 1984, and the first experimental demonstration was done in 1988, which was based on tris bipyridine ruthenium 2 tetrafluoroborate complex in acetonitrile with tetraethyl ammonium tetrafluoroborate as the supporting electrolyte. The open circuit voltage, that is OCV, of the system was about 2.6 volts, which was very much larger or significantly larger than that of most aqueous RFPs. Other non-aqueous RFP systems based on ruthenium acetyl acetonate, uranium beta diketonates, vanadium acetyl acetone, chromium acetyl acetonate, and manganese acetyl acetone have been recently investigated. Three types of membranes, such as first, anion exchange membrane AEM, second, cation exchange membrane CEM, and third one, that is non-ion selective membranes, were studied in an H cell with carbon cloth as the electrodes for non-aqueous RFPs. Non-aqueous RFPs have three main components. These are electrolyte, electrode, and membrane. Comparison between aqueous and non-aqueous RFPs. The major differences in the three components between aqueous and non-aqueous RFPs are summarized in this table. Electrolyte is the most essential component in all RFPs, which dictates the overall performance of RFPs. It consists of a redox couple, solvent, and supporting electrolyte. For non-aqueous RFP systems, major efforts are being made on electrolyte development by exploring suitable redox couples with compatible supporting electrolytes. In non-aqueous RFPs, metal ligand complexes are normally used as redox couples, which provide good reversibility and moderate solubility in organic solvent. Single metal ligand complex has been largely studied where the same electrolyte was used in both half cells of RFB's cells. Generally, the charging of RFP will convert the neutral single metal ligand complex to two oppositely charged species, and hence the redox crossover of non-aqueous RFPs may behave similar to that of metal-based aqueous RFPs. The redox diffusion through the membrane can reduce the Coulombic efficiency. However, it will not require the generation of negative and positive electrolytes in non-aqueous RFPs during the lifetime of the battery. Non-aqueous electrolyte RFP system. As discussed in our previous slide, non-aqueous RFPs can be classified through their redox couples and an electrolyte. The schematic of a non-aqueous RFP system is shown in the figure. While charging process, the electrical energy is stored as chemical energy in separate electrolyte reservoirs, whereas while discharge, the analyte solution is pumped into the non-aqueous RFP system, which flows through the porous electrode, where the redox couples dissolved in the analyte reacts on the electrode to generate electrons. These electrons carried away to the external circuit. The charge carrier species pass through an IEM or separator, which allows for the separation of the analyte and catholyte compartments. The general redox reactions in the discharge mode can be represented as at positive electrode m ln to the power z plus x plus minus x electrons charges or discharges to give m ln 2 plus. At negative electrode m ln z minus y plus y electrons charges or discharges to give m ln z plus, where m is a transition metal, L is a ligand, and N is the number of ligands. Furthermore, ionic liquid as the supporting is added to electrolyte to improve the electrolyte conductivity. In various non-aqueous systems, tetraethyl ammonium tetrafluoroborate TEABF4 is being utilized as supporting electrolyte due to its compatibility with organic solvents. An anion exchange membrane is considered to be suitable for non-aqueous RFPs because the anion of the supporting electrode or electrolyte such as BF4 minus or PF4 minus can easily pass through such membrane to maintain the charge neutrality. On the basis of metal ligand complexes available, several non-aqueous RFPs were designed and developed for commercial applications, which will be discussed in the further slides. Ruthenium complexes RFP. Matsuda and co-workers first proposed a non-aqueous redox system based on tris 2,2' bipyridine ruthenium 2 tetrafluoroborate, that is RuBPY thrice of BF4 2 complexes in an organic solvent, acetonitrile CH3CN with tetraethyl ammonium tetrafluoroborate TEABF4 as the supporting electrolyte. The redox reactions of Ru5 or Ru6 and Ru4 or Ru5 at the positive and negative electrodes takes place respectively as shown in the figure below. There are certain reactions which governs this mechanism explained as follows. At positive electrode, RuBPY3 to the power 2 plus minus 1 electron charges or discharges to give RuBPY3 3 plus with the E naught is equal to 1 volt versus AgCl. At negative electrode, RuBPY3 plus charges or discharges to give RuBPY3 2 plus 1 electron with E naught is equal to minus 1.6 volts versus AgCl. The expected open circuit potential or OCP for such system is approximately 2.6 volts. Here, the effect of various membrane materials such as sintered glass, an anion exchange membrane, a porous polymer hybrid membrane, and a porous fluorocarbon resin filter were studied for non-aqueous RFP. It was observed that a single cell assembled with each membrane discharges at a constant current of 1 milliampere in the H-type cell after a 50% SOC at a constant potential of 1.1 volts. The Coulombic efficiency varies with the membrane types in the discharge mode. Furthermore, it was also observed that the porosity of the membrane affects the efficiency of the system. That is, when a membrane that has small pore size polyflon filter applied to the non-aqueous RFP results in relatively higher efficiency during cell operation. Ruthenium acetyl acetonate redox flow systems. Another non-aqueous RFP system based on RU complexes was also investigated, which used RU complexes redox flow system, ruthenium acetyl acetonate RuACAC3 dissolved in acetonitrile containing TEABF4 in a H cell where graphite felt was used as electrodes and an AEM as separator. The RuACAC3 redox flow cell is shown in the figure below. Employing the Ru3 or Ru4 redox couple as negative reactants and the Ru4 or Ru5 redox couple as positive reactants. The redox reactions at the negative and positive electrodes are as follows. At positive electrode, RuACAC3 minus an electron charges or discharges to give RuACAC3 plus, with E0 is equal to plus 1.27 volts versus AgQRE. At negative electrode, RuACAC3 minus charges or discharges to give RuACAC3 plus 1 electron with E0 is equal to minus 0.5 volts versus AgQRE. The cell potential for this system is expected to be 1.77 volts. This system provides higher value of efficiency due to high solubility and stability of ruthenium acetyl acetonate caused by acetonitrile electrolyte. While charging, opposite charge species are produced and hence this might reduce the efficiency slightly due to crossover through the AEM. However, the loss of efficiency due to the crossover of redox couples does not affect the Coulombic efficiency as much due to oppositely charged species produced during charging reverted to the same reactive species. The ruthenium bipyridine and ruthenium acetyl acetonate redox RFP systems are dissimilar in terms of their charge species after charging, where the charge species of both tend to revert to the same initial state of the electrolyte, resulting in improved efficiency of redox flow systems during discharge. Now let us discuss about the vanadium complexes RFP. Vanadium acetyl acetonate has been widely studied as a single metal non-aqueous. The figure shows that the vanadium acetyl acetonate redox flow system using acetonitrile and TEABF4 was developed to be an H-type cell assembled with graphite electrodes and an AEM. This system shows three oxidation states for the redox reaction, and the same electrolyte containing The vanadium acetyl acetonate exists in both the analyte and the catholyte compartments. During discharge, vanadium acetyl acetonate is oxidized to VACAC3 plus at the positive electrode and is reduced to VACAC3 minus at the negative electrode. Hence, the reduction in Coulombic efficiency because of the cross contamination of the electrolytes can be improved using the same electrolyte in both the compartments. For this system, the cell potential observed was approximately 2.18 volts and Coulombic efficiencies of 50% at a 50% SOC. As the two redox couples degenerates to the same state of oxidation in the discharge mode, hence a large cell potential and a low crossover are obtained in the non-aqueous VACAC3 redox system. The redox reactions at the negative and positive electrodes are as follows. VACAC3 minus an electron charges or discharges to give VACAC3 plus with E0 is equal to plus 0.46 volts versus AgAg plus. At negative electrode, VACAC3 minus charges or discharges to give VACAC3 plus 1 electron with E0 is equal to minus 1.27 volts versus AgAg plus. Chromium complexes RFP. Chromium third acetyl acetonate CrACAC3 is another single metal flow cell based on non-aqueous RFP, which was initially developed by using acetonitrile supported by TEA BF4. The schematic of such a system is shown in the figure. In order to test the charge-discharge performance, a H-type cell was prepared with a graphite electrode and an AEM as the separator. The cell potential of the CrACAC3 redox flow system observed was 3.4 volts for an 1 electron disproportionation, and the Coulombic and energy efficiencies obtained were in the range of 53 to 58% and 21 to 22% respectively at a 50% state of oxidation for the electrolyte. This system has slightly higher potential, basically has slightly higher cell potential than an aqueous system. Hence, the solubility of CrACAC3 in acetonitrile might be a further challenge in improving the energy density. The redox reaction of the Cr3 or Cr4 redox couple at the positive electrode and the Cr2 or Cr3 redox couple at the negative electrode takes place as follows. At positive electrode, CrACAC3 minus an electron to give CrACAC3 plus with E0 is equal to plus 1.2 volts versus AgAg plus. At negative electrode, CrAcAc3 minus gives CrAcAc3 plus 1 electron, with E naught is equal to minus 2.2 volts versus Ag plus. Manganese complexes RFP. The manganese complexes, such as all manganese 3 acetyl acetonate MnAcAc3 redox flow system in acetonitrile and TEABF4 were also investigated for non-aqueous RFP system. In order to accomplish the experiment, a H-type cell was assembled with the same electrode and membrane as the CACAC3 redox system, developing novel redox couples using metal ligand complexes. The schematic of such system has been shown in the figure below. The redox reaction of Mn3 or Mn4 couple at the positive electrode and Mn2 or Mn3 couple at the negative electrode are as follows. At positive electrode, MnAcAc3 minus an electron gives MnAcAc3 plus with E naught is equal to 0.7 volts versus Ag plus. At negative electrode, MnAcAc3 minus gives MnAcAc3 plus an electron with E naught is equal to minus 0.4 volts versus Ag plus. For a 1 electron disproportionation of MnAcAc3, this system provides a cell potential of 1.1 volts and an efficiency of up to 21%. As discussed above, since this cell potential is lower than other non-aqueous RFP systems, hence further studies are required to solve the problems by modifying the ligands and the solvents employed. Nickel and iron complexes RFPs. Tri-2,2-bipyridine nickel 2 tetrafluoroborate and tri-iron 2 tetrafluoroborate were used to develop a non-aqueous RFP in a propylene carbonate PC solution and TEABF4. The reactivity and the kinetics of this flow system for the electrochemical reaction as per electrode type. Example: platinum, IR, nickel, copper, molybdenum, niobium, cobalt, and titanium were evaluated by cyclic voltammetry or CV. As shown in the figure, the best reversible reactions of Ni0 or Ni2 and Fe2 or Fe3 takes place at the molybdenum and nickel electrodes respectively. The redox reactions at the negative and the positive electrodes are as follows. At positive electrode, FeBpY3 2 plus minus an electron gives FeBpY3 3 plus with E naught is equal to 0.4 volts versus Ag plus. At negative electrode, NiBpY3 gives NiBpY3 2 plus 2 electrons with E naught is equal to minus 1.5 volts versus Ag plus. In this redox flow system, the cell voltage difference between the two redox couples observed was 1.9 volts, which is quite significant. Consequently, in comparison to previous catalyst or precious catalyst, which is a platinum, some non-precious metals such as nickel and molybdenum have potential as electrodes for metal ligand complex redox couples in non-aqueous RFPs. Samsung Electronics in South Korea have designed and developed same redox flow systems using NiBPY3 BFO4 2 and FeBPY3 BFO4 2. The values of cell potential observed for Fe2 or Fe3 and Ni2 or Ni0 were 0.65 and minus 1.66 volts on a glassy carbon electrode by measured by cyclic voltammetry. Nickel and iron complexes combined with tri-2,2' bipyridine provided a cell potential of about 2.25 volts. The charge-discharge process of this system was performed in a flow-type cell containing carbon felt as the electrodes and AEM as the separator and a dual electrolyte. For example, zero point 0.2 molar NiBPY3 BF42 and zero point 0.4 molar iron or FeBPY3 BF42 in PC with TEA BF4 0.5 molar. It represents a higher initial coulombic value of 90.4% and energy efficiency of 81.8% in comparison to the aqueous system. Uranium complexes RFP. A non-aqueous RFP based on uranium complexes as the negative and the positive electroactive material in polar aprotic solvents was proposed, as observed from the figure. In this system, uranium complexes were prepared by combining beta diketonates, which consists of various ligands including hetafluoroacetylacetone, heptafluorobutanol, pivolate pivolloyl trifluoroacetone, acetyl acetone, and dipivaloyl methane, and dissolving the complexes in polar aprotic solvents such as acetonitrile. The solubility of U6 and U4 complexes higher than 0.8 molar and 0.4 molar respectively were obtained due to high solubilities of the uranium beta diketonates in the polar aprotic solvents. The open circuit potential was observed to be approximately around 1 volt for the AC-AC ligand by using the U6 or U5 beta diketonates solution as the catholyte and U4 or U3 beta diketonates solution as the anolyte. The redox reactions at the negative and positive electrodes are as follows. At positive electrode, UO2 ACAC2 minus an electron gives us UO2 ACAC2 with E0 is equal to minus 1.45 versus FC plus. At negative electrode, UACAC4 minus gives UACAC4 plus an electron with E0 is equal to minus 2.45 volts versus FC plus. Cobalt complexes RFPs. As discussed previously, metal ligand complexes can be classified into two types of ligand complexes, such as acetyl acetonate complexes and 2,2-bipyridine complexes. However, a third group of complexes, that is bis-acetyl acetone ethylene diamine complexes, has been developed recently. A new single metal non-aqueous redox flow system employing a cobalt 2 bis acetyl acetone ethylene diamine, which is COACACN electrolyte supported by a TEA P16 in acetonitrile has been investigated, which has been explained in the figure below. The COACACEN redox system was developed with a graphite as an electrode and an EM as the separator. The redox reaction at the positive and the negative electrodes was examined on a glassy carbon electrode as follows. At positive electrode, COACACEN minus an electron gives us COACACEN plus with E naught is equal to minus 0.2 volts versus Ag plus. At negative electrode, COACACEN minus gives us COACACEN plus 1 electron with E naught is equal to minus 2.2 volts versus Ag plus. This system provides a cell potential of approximately 2 volts for single disproportionation and Coulombic efficiency of 90.24% in cycle 5. Furthermore, the effect of environmental factors such as temperature, oxygen, and water are evaluated and observed that oxygen and water causes degradation in the efficiency of non-aqueous RFP systems. Hence, elimination of oxygen and water is essential in order to achieve a high-performance non-aqueous RFPs. Operational parameters and performance of all non-aqueous RFP systems. All non-aqueous RFP technologies and their important parameters are summarized in this table, which is comparing the all available non-aqueous RFP systems. So students, let us summarize what we have learned till now in this module. We have learned about the aqueous RFB batteries. These batteries showed low energy density of about 20 to 50 watt-hour per L due to aqueous electrolytes. The energy density of a RFP depends on cell voltage and the solubility of redox compounds. For aqueous RFPs, the cell voltage is limited. That is, it is around 1.2 volts by the narrow electrochemical window of water that breaks down with less than 1.5 volts. However, the non-aqueous RFPs utilized organic electrolytes that offer significantly wider electrochemical window, for example, above 5 volts, and larger solubility for redox compounds, thus provide larger value of energy density. Furthermore, as non-aqueous RFBs use organic solvent that provide low freezing point. Hence, due to this reason, their working temperature can also be extended. Several non-aqueous RFBs based on metal ligand complexes were successfully developed. Thank you.